but let's introduce Joe. So it is a pleasure to introduce you today Joe Anderson. Joe is originally from the UK, where he got his PhD at John Muir University in Liverpool, but he soon moved across the ocean and across the equator to Chile. He first started as a postdoc at the Universidad de Chile in Santiago, working with Mario Amui, and then he became an ESO fellow in 2013. Today, Joe is still at ESO, but he's working as a support astronomer and instrument scientist for Force 2 at VLT. And Joe is an expert in supernova explosion. He likes a lot hydrogen-rich supernova that I know, and he works a lot trying to linking supernova explosion with their progenitor. And I'll leave it to you, Joe.
Okay, thank you, Giacomo. So yeah, this talk is going to be on constraining supernova progenitors, constraining the progenitors of massive star explosions, and then on a very specific thing on the core collapse supernova 56 nickel yields. And so on this talk, when I talk about this subject, I like to show the kind of the main or the only results plot from this specific paper that I'm going to be discussing on the title slide. So I'll show this here. Then I'll go through and give a background, give the introduction to this whole topic and come back to this. But I show this here to already motivate you thinking about what I'm going to show here. So this is a very simple plot. And this is a very simple analysis that I did here. This is just compiling everything in the literature, all different values that people have published for ejected nickel 56 masses for different core collapse supernova types. So on the x-axis here, you have nickel 56 mass. And on the y-axis, and so these are the cumulative distributions for the different types. So I'll go into what this means. I'll go into the different supernova types on the next slides, etc. But the main result I'm going to be discussing, and again, try and convince you of the importance of this result for understanding supernovae, but also scientifically in general, is the fact that you see in this black distribution here is significantly biased to low values of nickel 56 compared with all these other supernova types, and specifically also compared with the combined sample of these other types, which I named strict envelope supernovae. So this purple curve here. So, okay, so I'll come back to this plot, but hopefully that's already got you thinking about what I'm going to present here, and you already have questions about what this means, etc., etc. But core collapse supernovae, what are we talking about here? We're talking about massive star explosions that explode through this core collapse supernova mechanism. Massive stars. Here we're talking about things that are more massive than 8 to 10 solar masses, around those masses. These massive stars throughout their lives go through successive stages of nuclear burning until they get to the end of their lives with an iron core. When they have an iron core, it's no longer energetically favorable to keep fusing to heavier elements. The iron core keeps growing, keeps growing. It keeps growing until it can no longer support itself against the gravitational collapse of the core. So the degenerate pressure can no longer balance gravity. And at this point, this is what we know, what we refer to as core collapse. So you have this iron core, this starts to collapse inwards. This keeps collapsing, and this is shown in this kind of cartoon on the right-hand side here. This keeps collapsing until the collapse reaches nuclear densities, and then you have a bounce of that collapse. That bounce of the collapse then produces a shock that then traverses through the inner layers of the star. And it was initially thought many decades ago that just this initial bounce and this initial shock could produce these explosions, could eject the outer layers of the star. But then it was seen and it was concluded that this shock will actually stall. And what's thought now, or the main understanding, the main model to explain how core collapse supernovae do actually eject their outer layers, is that this shock is revived through a capture of the huge neutrino luminosity that's produced at the center of this explosion. So where you have some compact remnant, so either a neutron star or maybe later a black hole, you have very dense material. The interaction of these materials, it produces a huge neutrino flux, and somehow the outer ejector, the inner ejector near the center of the star is able to capture this huge neutrino luminosity, and this revives the shock, and then the shock propagates out through the rest of the star, ejects the rest of the star, and we have what we know as supernovae. So these are bright transients that we observe on the sky. So this is the model we have for understanding how massive stars explode. We're pretty confident that this works. This is what is actually happening in nature. There's various reasons we're confident in this, various pieces of evidence that back this up. But what are the actual supernovae that we see? So that's the theoretical model for what actually is happening here. But what we see on the sky, we see transient objects in the sky, right? We observe the sky one night, we observe a galaxy, and it's just the same galaxy that has been there for the last days, weeks, months, years, etc. And then suddenly we see a new star, a supernova. So it's usually a point source on top of the galaxy, which can be really bright. It's usually really bright on top of the galaxy light. And then we try and classify these objects. Classification is generally done, or the classification scheme that I'll show here is optical spectroscopy, obtained as close as possible to explosion, but this means, and historically this means, you know, within several weeks of initial explosion, we obtain an optical spectrum, and then we classify these supernovae. And this classification scheme is shown here, which is the standard thing that's shown in many different talks here. In the first initial classification, you separate into type 2s, which show strong hydrogen lines in their feature, in their spectra, and type 1s that don't show those hydrogen lines. In the type 1s, we also have 1As, which are believed to come from white dwarfs in a binary system, white dwarf explosions, but I'm not going to discuss these at all in the rest of the talk. In the type 1s, there are also these 1Bs and 1Cs, and also type 2Bs. So as I said, a type 2 shows strong hydrogen features in their spectra, but then as you move to the type 2Bs, these show short-lived hydrogen features in their spectra, and then 1Bs show basically no hydrogen, except in some special cases in the spectra, and then going to the 1Cs, you don't see any hydrogen, you don't see any helium. And so there's these other core collapse types here, and if you look at, you know, people presenting classification schemes in general, you can keep going and subclassify these into many different things, etc. But for the purpose of this talk, I'm just separating things into type 2s, and then this other family, which are called stripped envelope supernovae, type 2Bs, 1Bs, and 1Cs. At the bottom here, you should see the typical spectra of these. So the type 2s here, dominated by these Balmer series, strong hydrogen lines, 1Bs, no hydrogen, but strong helium, 1Cs, no helium, and then these 1C broad lines, which are kind of stretched out spectra of the 1Cs. And so you see these broad spectral features here. So this implies large ejector velocities producing these broad spectral features. And already on the right hand side here, we can start to link this to what's the actual progenitor is. So if we don't see hydrogen in the spectra, then we assume this is because the progenitor is intrinsically poor in hydrogen, and therefore we go from something that has hydrogen to something that has no hydrogen but still helium, and then something in 1C that probably has no hydrogen and no helium. So this is the classification scheme that we're generally working with when we're discussing core collapse supernovae. Now, as I said, I'm going to group, for the basis of this talk, I'm going to broadly classify things into hydrogen-rich type 2 supernovae, and then stripped envelope supernovae, so all the other ones that we think are core collapse supernovae that don't show hydrogen. The type 2s are the most common stellar explosion that we see in the universe, and they show this characteristic plateau in their light curves, which I show here on this bottom plot here. So there's lots of labels on here, but this doesn't really matter. The main thing to see here is that, so this is the light curve, so this is time past explosion on the x-axis, absolute V-bang magnitude on the y-axis, and you see after this initial peak, you have something we call the plateau here, and then you have a significant drop about 100 days, and then this linear decline here. This is characteristic plateau in this light curve. And these different phases here is understood as being due to the light curve being powered by different mechanisms. And this is important to know because this is a big difference between these type 2 supernovae and the stripped envelope supernova that we'll discuss next. So initially with a type 2 supernova, you have this large hydrogen envelope. As the shock propagates out through that hydrogen envelope, it ionizes all this material. And this means that the initial decline in the light curve and the plateau is basically being powered by shock energy and also the recombination of that hydrogen. And you have a recombination wave that goes inwards in mass coordinate throughout the ejector. And once that wave gets right through the hydrogen envelope, then you have this drop off of the light curve here, and you get onto this tail part of the light curve here, where we believe this tail is almost exclusively powered now by radioactive material that's produced in the explosion. So in the type 2s, you have these transitions between different powering sources. It also shows some example spectra here, which again in the top you see at early times this is dominated by the Balmer series, dominated by strong hydrogen features at later times. So this is now at 72 days past explosions. You see many different lines, many metal lines, etc. So that's the general picture, but we see a large diversity in type 2 supernovae. So large diversity in the light curves and also in the spectra. Show this on the bottom left here. So this is again absolute V-band magnitude light curves. You see this large range in different luminosities of the events. You see things that are declining at different rates. You see things that have this plateau, which is quite short or longer, etc. In the spectra here, what I show is these spectral evolution for a large sample of supernovae here. So each blue kind of connected dots is one supernova, and this is for different spectral lines in the spectrum. So velocity on the y-axis, days past explosion on the x-axis. So this again shows a large range in velocities within the different supernovae, and there's also a diversity in when these different lines appear or disappear from the spectra, etc. And so all this diversity is being produced by, we think, some differing pre-supernova structures that exploded together with these different possible explosion properties. So moving on to the hydrogen pore stripped envelope supernovae. So as I say, these are the types 2b, 1b, 1c, and 1c broad lines, where the reason they're stripped envelope is we don't see evidence for hydrogen in their spectrum, and we see a lack of Balmer lines, a lack of the Balmer series. I show one example here. This is one very well observed type 2b supernova, supernova 2016 GKG. So in the spectra on the right-hand side here, you see this is a type 2b. So as I said, at early times, there is some evidence for H alpha here. So you can see my mouse here, I hope here. But after a few weeks past explosion, so this is together with a few other similar supernovae, this H alpha disappears, and this is replaced by other features, and the spectra starts to be dominated by helium features. This is understood that these type 2b's just have a thin layer of hydrogen intact when they explode. And as you go to the 1b's and 1c's, as I said, this layer is even further reduced. The light curve on the right-hand side, on the left-hand side here, this is a key difference. This is a clear different morphology between the light curves I show here, which have this plateau phase at early times, whereas here you have this kind of characteristic bell-shaped light curve. And most stripped envelope supernovae have a similar light curve to this. Also 1A's have a similar light curve to this in terms of the shape. And this is characteristic of the whole, most of the light curve, the powering mechanism, the luminosity is being dominated by radioactive decay. You see something interesting going on at very early times, which we won't discuss here, where you see these kind of early cooling phases here in this specific supernova. They say presence, a lack of spectral lines, which indicates an increasing sequence of stripping of the envelope before the explosion, compared with the type 2s that have most of this envelope still intact. But you still see still observe diversity in stripped envelope supernovae. So in this plot here, you see many tens of different supernovae here. So you see diversity in terms of how bright these things are. And it's possibly difficult to see here, but also in how kind of wide these light curves are, etc. But they all have this characteristic shape, right? And this is the characteristic shape because this is being powered by radioactive elements that produce an explosion in the center of the star. And that radioactive material is decaying, and that emission from the decay is then diffusing out and powering these light curves. So in general, stripped envelope supernovae, they do show a diversity, but I would argue less diversity than what's seen in the type 2s, and they're clearly just different from the type 2s. In the spectra, you do see some diversity. I mean, this is the whole point. There's classified into different events depending on the presence or lack of different lines, but in general, they're still somewhat similar. Okay, so first I discussed very briefly the explosion mechanism, how these things explode, how these are thought to explode. And I've gone through the different classifications of the different events that we observe on the sky. And so I think, as Giacomo said, this is kind of my main area of research, is trying to do this mapping from massive star progenitors to massive star explosions. But I think this is also one of the most important questions in understanding supernovae. As the cell supernovae are very useful for understanding many other areas of astrophysics because they're so bright and we can observe them to large distances, etc. But actually observing the supernovae themselves, we want to know what type of a star explodes as what type of supernovae. So we observe this diversity even within the classes. And so the question is, how is this diversity produced through different explosions of different progenitors following different evolutionary paths? So you start off obviously with some pre-supernova progenitor, which is dependent on the initial conditions. So then the zero-age main sequence mass, the birth of the star, the presence of a close binary companion. So whether the star has a close binary companion, what the parameters of that binary setup is between the two stars, the progenitor metallicity, the progenitor rotation, and other parameters. Then this evolves through stellar evolution. And the main thing that happens that's important in terms of the classification that we get to at the end, at least of first order, is how these different initial setups will affect the star during its evolution through different mass loss mechanisms. So whether that's binary mass stripping, whether that's steady winds that occur through the lifetime of the star, going through the different stages of its evolution, or whether these eruptive winds, things happening on shorter time scales in an explosive manner. So all of these removes mass from the star. And then dependent on the amount of mass that's removed from the star, this leads to the supernova type classification. And that's the difference between supernovae type 2 and stripped envelope supernovae, is the amount of material stripped before explosion. And so when you get to explosion, you get to that time that the core starts to collapse, then you have some pre-supernova progenitor with some density structure determined by all of these previous processes that's then exploded with some explosion energy, which is dependent on the conditions in the core at that moment of collapse. The explosion also produces a significant amount of radioactive material, and the focus later on this talk is the nickel 56 production. Something that I won't talk about here, but is extremely important, and I think within the last 10 years, we've kind of realized this is important, possibly in many more supernovae that we thought it was important, is what can also change what we see on the sky in the supernova transient behavior is also the interaction of this ejector of the star with any material around that star. But as I say, I won't discuss this for the rest of this talk. So yeah, massive star progenitors, core collapse supernovae. Again, there's separation between type 2 supernovae and stripped envelope supernovae. So most core collapse supernovae arise from stars with initial masses between 8 and 30 solar masses. I mean, this is the statement. It's kind of obvious. This is just mainly determined. It's possible that higher mass stars explode as core collapse supernovae. It's possible that they don't. It's possible that they do something different. But also just dominated if we talk about rates, just because of the shape of the IMF, nearly all things that we observe are going to be within this range, and dominated by the lower mass progenitors. Type 2 supernovae, we've been pretty sure for a number of decades that these are red supergiant stars, these stars that retain a significant fraction of the hydrogen envelope at the moment of explosion. And I'll go on to the next slides of constraints that show this. Stripped envelope supernovae, so these also massive stars, but have been stripped of their envelopes. So the question is, how are these stripped of their envelopes? And there's basically two main ways that you can do this. They can be single stars. If they're single stars, then they generally probably need to be higher than 25 solar masses in order that the winds are strong enough in that single star setup to remove the outer envelope. And still then, it seems like that's difficult for single stars. But we know such stars exist, we observe them, although they're relatively rare compared with the rate of stripped envelope supernovae. The other option is massive stars in binary systems. So the difference here is that if you have a star in a binary system, then you don't have to rely just on the winds to remove the outer envelope. And this means that stars with initial masses less than 25 solar mass can explode with their envelopes stripped envelope supernovae. We also know that the majority of massive stars are expected to interact with a companion and thus affecting their evolution. Okay, now I have a couple of slides on just what the core collapse supernova progenitors constraints are, a summary of the literature. So the most direct way of getting information here is, a supernova explodes, and then you go and see, pre-explosion, if there is anything there in archival images. And this has been reasonably successful for type 2 supernovae, where we have quite a few constraints where all the progenitors are consistent with being red supergiants or yellow supergiants within this mass range of 8 to 20 solar masses. It's a bit strange that we don't see something above 20 solar masses, because we do see red supergiants in the local universe above this mass, and this is named the red supergiant problem, which is a very interesting topic, but not something I will discuss further in this talk. And then stripped envelope supernovae, the problem is here we just have very few detections. So we have quite a few non-detections, but they're not so constraining. I mean, one can use those to argue for low mass progenitors, but it's also difficult because these progenitors, Wolf-Rayet progenitors, are likely to be very blue. and most of the archival images is usually at redder wavelengths, V-band, etc. But we have very few detections, and the possible detections we do have are consistent with things being, in general, lower than 20 solar masses. We can also model the observations, model the light curves and the spectral evolutions of these things. So this is done through various different ways, where you can take progenitors from some stellar evolution codes, such as MESA. You can explode these and then follow the resulting transient behavior, and then compare these to observations. And this is something I show here on the bottom right here. So this is work with the student Laureano Martinez, who's working with myself and Melina Burston, where we're taking a large sample. So this, I put 2020 here actually, but this plot is not published. So we're working on a large sample of about 70 type 2 supernovae, where we model the supernovae in terms of their bolometric light curves and their velocities, and extract the physical parameters. This is something that's been done by many of us as well. And there's also various analytic prescriptions that one can apply to observations of the light curves to try and extract physical parameters. And so for type 2s, the problem here is you have a large degeneracy between various physical parameters and a large range of constraints by different groups. And some of them, because these results are consistent with the direct detections from above of being relatively low mass massive stars, but some of them are not. And some codes, some work constrain some of these type 2s to be pretty massive initial mass stars. We hope to shed some light on this work that we're doing in Laureano, that hopefully will be out in the next few months or later this year. The stripped envelope supernova, the most common way of extracting parameters is applying analytic modeling, and specifically RNet modeling, and I'll come back to this because this is used in the results that I show in this paper. And you can apply this modeling to extract nickel masses that I will show later, but also ejector masses. And when you do that, then the ejector masses are kind of consistent in most cases, in not all cases, with less than 20 solar mass initial mass progenitors. Another couple of ways you can constrain progenitors is through nebulous spectroscopy. So nebulous spectroscopy is obtaining spectroscopy once the outer envelope and outer ejectors become optically thin. And then when you take these observations, you're seeing down into the inner core material, where the inner core material was produced during stellar evolution, was produced during the explosion, etc. And so, you know, the strength of lines that you see, for example, in that nebulous spectroscopy, then gives you some indication of what the initial mass of that star was, because the core at the moment of the explosion is highly correlated with the initial mass of the star. And I showed this one example here. This is the paper we wrote a few years ago. So we worked on this Supernova 2015 BS, and specifically used this oxygen line here, where you see this one has this big booming oxygen line compared with these others here, and we use this to conclude that this is a relatively massive progenitor for this one specific one here. But the important thing is here is the rest of them have quite weak oxygen. So again, the type 2s are consistent through this nebulous spectroscopy, with most things being consistent with progenitors of less than 20 solar masses. Stripped envelope supernovae, most constraints are also consistent with 20 solar masses, but again, there's some room for some specific cases, and also most likely the 1C supernovae, or possibly some of them coming from more massive progenitors. Finally, although this doesn't include all the different constraints on these two slides here, but environment constraints. So what does that mean? It means comparing the host environment properties, so where the supernova exploded, what type of galaxy that's in, or what the properties of the local stellar population where the supernova exploded, comparing these between different supernova types, for example, the association to young star formation, massive star formation, or the age and metallicity of the host stellar population. When you do this, you generally find that the environments of stripped envelope supernovae are found to be younger and more metal rich than type 2 supernovae, specifically the type 1Cs in both cases. So younger and more metal rich environments, which one can conclude, therefore the progenitors are also younger and more metal rich, which is shown in this plot here, but I'm not going to go into the details of this because this would take too much time to explain. Okay, so a kind of summary of them then on core collapse supernova progenitor explosion constraints, and then some open questions that I think are interesting. So my opinion is that most analyses, putting these different analyses together, suggest similar initial mass progenitors between most supernovae type 2 and stripped envelope supernovae. So I highlight most in both these cases because, in my opinion, there's still room here for some differences, and there's still room for at least some of the stripped envelope supernova population to come from initially more massive stars and more metal-rich progenitors than supernovae type 2. And this is the second point here. But however, the fact that I'm saying that probably most of them have similar initial progenitor properties, then this leads to the conclusion that binary interaction must be playing a significant, if not dominant, role in producing this difference between supernovae type 2 and stripped envelope supernovae, in that stripped envelope supernovae have been stripped of this outer material. Whereas, because if they were just coming from single stars, then you would expect generally the population to be biased towards much more massive stars. So some questions that I've written here, this isn't the full set of questions, but one we want to ask, this is the things that I thought when I was writing down that I find interesting is, what is the exact mapping of progenitors supernova types? I mean, I think we'll be spending years before we have this, but this is always the goal and an overall goal of thinking lots of this research. Do single massive stars more than 20 solar masses explode as supernovae? So those stars exist, and so we might say yes, but it's possible that some of those massive stars fail to produce bright explosive transients, and there's actually some evidence for this, both in models, explosion models, and also some observations as well. So trying to work out that where that limit is, where you stop producing supernovae and you start producing things that implode but don't actually produce a transient, I think is interesting. So how much binarity interaction affects the type 2 diversity? So type 2s can basically be explained through single star evolution, because you retain all the hydrogen envelope, etc. But you still expect, just because lots of these stars are in binaries that are going to interact, you still expect binary interactions to play some role, and maybe playing some role in the diversity I showed earlier. And then what is the fraction of stripped envelope supernovae that explode from effectively single stars? So if we're concluding most of them come from binaries, do some of them still come from single stars, and what is that fraction? And then a kind of separate but more general question, what is the heavy element yields of the different supernovae, different massive star explosions? And, this is really important then for understanding many other things in astrophysics. Because supernovae, core collapse supernovae, and all the type 1a supernovae, the main heavy metal producers in the universe. Okay, so now specifically go on to this thing that I've been mentioning at the start and been mentioning throughout this talk now and then, nickel 56. So how can we use nickel 56 as an explosion or progenitor constraint? And so the first question is, why nickel 56? Why not something else? What's the importance of this one specific isotope that I'm mentioning? So specifically here, you see in top left here a plot. So this is from Spectral Evolution explosion models. And so this on the x-axis is the interior mass. So as you go in this direction to the right, this is going further out in the star. And this is central to the central part of the star here. So the central solar mass here. This is mass fraction. And you see in the very central part of the star, so there's many elements that are not on here, many things that would be down here, etc. You can find other plots that are much more complicated than this. But the key important thing here is that, in the central, like 1.5, 1.6 or something like this, solar masses, nickel 56 is the dominant thing that's produced here in explosions, in the explosion. So it's produced at significant mass here. This is also, so this is from predictions from stellar evolution, from explosion models. On the right-hand side, we see the constraints for the famous supernova 1987 A, where in the middle you have this nickel 56 constraint that 0.07 solar masses was produced. And in this case, for this supernova, this is really well constrained because this was so nearby. This has, amazing data for this supernova. And the important thing is if you compare to these other isotopes of nickel 57, nickel 58, so they're much lower in mass. And the other important thing is the timescales. So the decay chain is nickel 56 to cobalt 56 to iron 56. And the decay chain, the timescales here are kind of extremely relevant for the timescales over which we watch as we observe supernovae. So it's really the decay of nickel 56 which dominates the energy input from radioactive decay for at least the first several months, several years of core collapse supernova explosion. So that's why nickel 56. And then because we see so much nickel, or we believe that core collapse supernovae produce so much nickel 66, then we say we can use this as a tracer of heavy element nucleosynthesis in core collapse supernovae, and this can give information on the inner core and the explosion. So, okay, getting closer to my my work here, my paper that I want to present here, and then the subsequent discussion of that. So, these supernova types are basically, very similar things in terms of their, how they've their initial parameters, how they explode in the core. They're very different in the outer structure that leads to this separation between type 2 supernovae and stripped envelope supernovae. So this last thing that I said, that they're very different, has led to them being analyzed separately. And this is understandable because, when you start doing sample analysis, you need to cut your sample somewhere. And, analyzing large samples is a lot of work, etc. Over the last decade, these samples, the last kind of 10 years, there's been quite a lot of large sample analyses. My work's mainly concentrated on the type 2s, but there's been lots on the stripped envelope supernovae. But they're always analyzed separately, and they always conclude and give things like nickel mass distributions, as I will show in the next slides. But because they're done in separate studies, then there's kind of there's not much formal discussion of how this comes together to understand the whole core collapse supernova picture. And I think this is important because if they're inconsistent, which I'll show that they are, I think this has implication, or this has something that we need to understand that will hopefully let us understand the core collapse supernova phenomenon in more detail, and also aid us in understanding how what the yields are, etc., etc. So as I said, there's been no kind of formal comparison between stripped envelope supernovae, nickel masses, and type 2 supernovae, although generally people have said, and if you compare the two papers, your stripped envelope supernovae are generally producing more nickel than the type 2s. The questions that you want to answer with this is, at what statistical level is this difference? And is this a real intrinsic difference, or is this a problem of how we're comparing the data, how these supernovae have been analyzed, etc.? If this is a true intrinsic difference in the nickel masses between the different supernova types, then what does this mean for their progenitors and how we can understand this? And then also, can explosion models explain these differences, and can they explain the values for the different distributions? So this led, this kind of informal discussion with people of, the stripped envelope supernovae, they have much higher nickel masses, the novas, and people, some people would kind of brush this away and say, yeah, okay, but this is understood, there's no problem with this. But again, there was no formal study outlining this. So this is what I decided to do in 2018, 19. But I should mention, this was first formally outlined in this paper by Kushner in 2015. Although his paper is still not accepted, and so I guess it will never be accepted because it's 2015. And also the main aim of that paper, or the main focus of that paper, was on explosion models comparing type 1a supernovae and core collapse supernovae. And so my guess is that's why it didn't kind of focus the community on this question, which I think since my paper has come out, that there has been significant discussion of the implications of this and trying to understand this. And I list a few of these papers here, one by myself and my student. I'll come to a number of others, and there's a number of others that has been discussing this as well. But this is extremely simple analysis. This is the simplest analysis you can basically do, because I didn't estimate anything myself here. And so there's a reason for this that I'll go into. So basically, I just searched the literature for all estimated nickel masses. So I did it very simply, going on to ADS and putting words in the abstract of supernova and type 2b, or supernova and type 1b, searching through all those abstracts, searching through the papers, and trying to collate nickel 56 masses that have been published. So this took several days just to do that, but it's very simple work to do. And I came up with this sample of 250 core collapse supernovae that can be separated in these different types, but basically, around 100 type 2 supernovae and around 150 stripped envelope supernovae when we total these up. So I had no preference for what the technique was used here. All values were compiled and averaged. So I can see, and I've had responses to this when I published this, and people saying, well, you should have analyzed everything consistently. There's so many, how can you compare these different samples even for the same supernovae? Because people use different techniques, people use different distances, people use different host galaxy extinction estimates. But my point was here in doing this is to say, okay, but this is what the community is publishing. And if the community is publishing consistently larger values of nickel masses for one supernova over the other type, this is important, even if there are systematic differences that can possibly explain those. I think we need to start talking about the fact that we're publishing these different nickel masses, and whether this is important, whether it's intrinsic, or how we can understand this. So there's various observational uncertainties that I've kind of touched upon. So distance, host galaxy redshift, bolometric corrections, so how you correct for the flux outside the bands in which you're observing these supernovae, and all the explosion epochs. So which is the date that you really believe, or you think, that the supernova exploded on. And then a key issue here is that for the different supernova types, because of their different evolution and their different light curves, basically, we estimate the nickel masses in different ways. So for type 2 supernova, we use the tail luminosity, and stripped envelope supernova, we use the peak luminosity. And I'll explain that now. So this goes back to this light curve that I showed previously. So again, time past explosion in days on the x-axis, absolute V-band magnitude on the y-axis. And as I said, once the hydrogen envelope is fully combined, so once you've got off this plateau, then during this tail phase, then we believe that this is fully powered now by trapping of the radioactive decay, the emission from the radioactive decay of cobalt-56. So it's cobalt-56 at this time, because by now the contribution from nickel-56 is negligible. And so the reason we can do this specifically for type 2s is if we look at the light curve here and we look at how fast the light curve is declining here, then in the majority of the cases, not all, as Giacomo will probably tell me because he had a paper on one that doesn't confirm to this statement, but in the majority of the cases, type 2 supernovae are declining at this epoch with a decline rate consistent with the full trapping of that cobalt-56 decay emission, full trapping of the gamma rays. So therefore, any point on here, we can basically say, okay, what's the luminosity here? What's the time since explosion? And we can calculate the nickel mass in this way. And I think that's really robust. I think it's hard to argue with the modeling kind of theoretical aspect of that. For stripped envelope supernovae, it's more difficult. It's more difficult because if we first just look at this tail here, in nearly all stripped envelope supernovae, when you get to this tail, it's the decline, the light curve is declining quicker than that predicted from the trapping of the cobalt-56 emission, and therefore you can do something here, but then you have to start modeling this. You can't just assume that this luminosity is directly basically the nickel directly related to the nickel mass that you want to estimate. So because of this, for the majority of the values in my meta-analysis, people have used what's known as our nets rule. And so this basically makes various assumptions about how the nickel, the energy from the nickel decay chain is deposited into the ejector, makes various assumptions about the properties of the ejector. And when it makes those assumptions, it says that the luminosity at peak equals the rate of energy production by decay at peak. So basically, if you know the peak luminosity, the bolometry luminosity, then this just gives you the nickel mass pretty much. And most of the studies in literature for the last 2 decades have basically used this to constrain the nickel mass for various objects. Yeah, this is one example in the bottom right, but I'll come back to this now, so I'll skip this now to save more time. So now, okay, so now we come back to this plot that I showed on the first slide here. So after doing this, collating all these literature values, and then combining these into distributions for the different supernova types here, then I come up with this community distribution. So again, on the x-axis, nickel-56 mass. So this is going from 0 on the left-hand side to 1 solar mass of nickel on the right-hand side. And these are cumulative distributions. The black shows the type 2s here. And then the various stripped envelope cases, one see broad-lined here. But for the purpose of this talk, I basically combine this to this purplish color here, the stripped envelope supernovae. And you can see, as I showed on the first, when I showed this, and I've been discussing, clear difference. The stripped envelope supernovae are biased towards producing, at least the observed distributions using this, our net rule, are producing much more nickel than the type 2s. Another interesting thing here to note is if you go down to the bottom left here, this is something I'll come back to, there's a real lack of stripped envelope supernovae producing very little nickel. And also, you see these huge values here. So why do I say they're huge? Because anything like higher than 0.3, 0.4, to 0.5, this is getting up to values that you produce type 1a supernova, where you completely incinerate the star, right, the white dwarf star. Whereas here you're leaving a compact remnant, a neutron star or black hole. So the amount of nickel that you can really produce is quite constrained. So some of these values seem crazy high here on the right-hand side. So this is kind of summarized here. So I'll try not to repeat myself here too much, but there's clear statistically significant differences. 0 stripped envelope supernovae with these lower values. I go to the bottom left here, whereas 50% of the type 2s have lower values, have values lower than 0.03. And these crazy high values here, they just seem way too high in terms of our understanding of how nickel is produced. in core collapse supernovae, and also when you compare to 1As. And then I just circle the median values here between these different two supernova types. So this is the, so the first kind of result here is an observational result that stripped envelope supernovae clearly produced for those observed and those published in the literature, which is important to make those the statements, but have higher nickel masses than type 2s. And then another interesting thing is if you compare to the predictions by neutrino-driven explosions, so these are the dominant types of explosions that we think are happening in core collapse supernovae, then core collapse, these explosion models really fail to produce anything much above 0.2 solar masses. And so these are the different references I have here for these gray lines that I have here. And in the thatched region is everything that's basically ruled out by these studies here. So for the broadline 1Cs, it's the majority of the population is producing more than 0.2 solar masses. But even for the other stripped envelope supernovae, it seems that they're producing, or they have estimated nickel masses. They're in excess of what explosion models can produce. So how may we try and understand this, and what's the importance of this? Can we understand this in terms of differences in the progenitors or explosions? Or is there some systematic in observations or in our modeling, in those errors, that produce this effect, and really there's no difference here? So for answering either of these questions, I think is important for our moving forward in studying supernovae in general. So if supernovae type 2 and stripped envelope supernovae arise from similar mass progenitors, then we may, I say may here, expect the nickel 56 yields to be similar. I come back later why this may not be the case, but this is probably the kind of naive, somewhat ignorant view, and this is what I was thinking back in 2009, also when I published this paper. But what is clear, if you do have different nickel masses, there must be something different, and this must imply differences at least in the core structure and the explosion properties. So either that's the case, some of the statements is the case, or maybe it's just an error in how we're calculating these nickel masses. So as I said, I think this is very difficult to find an error in the way we're doing type 2 supernova nickel masses, because I think that's pretty robust, and there's a couple of things that are possible there, but I think we've analyzed those, and I don't see those values changing so much. But for the stripped envelope case, yeah, there are systematics here. For example, how accurate is the Arnett's rule? And so this is before we published this work in 2019. This is something people have said for years. For stripped envelope supernova, our net rule probably overestimates nickel masses, etc., for various assumptions that it makes. And I'll go into the next slides from ways that you can maybe get around this. Can observational errors explain nickel 56 differences? So is this simply the way we're observing supernovae, the way we're observing samples, etc.? And this is linked to the last one. Are we missing the dimmest stripped envelope supernovae? So as I showed, if the nickel mass is for a stripped envelope supernova directly related to the luminosity of the event, which is what Arnett's rule basically says, because it says the peak luminosity directly related to nickel mass. So you go to lower nickel masses, then things will become dimmer. Dimmer things, as we know, are harder to detect, especially as you go to more distant places in the universe. And therefore, it's possible that we're just missing these really dim stripped envelope supernovae. And again, I'll come back to this. So as a follow-up on this, we had a paper out last year that was led by Nico Mesa. So this was actually a pre-doctorate analysis that Nico did with me on an internship at the ESO. Nico is now in California doing his PhD there. So the aim here was to, like I say, I'm pretty confident in what we're doing for the type 2s, for this, or what the community is doing for the type 2s. So the stripped envelope supernova is not so clear. So we thought, okay, we'll concentrate here on a well-observed sample of stripped envelope supernovae and rederive nickel 56 masses. So what's a well-observed sample was where we have very good cadence. So cadence being how frequent the observations are, and we have good wavelength coverage. So the wavelength coverage is on the y-axis here of these light curves, so these bolometric light curves. So again, time since estimated explosion on the x-axis. On the y-axis, the bolometric luminosity across these bands, B in the blue to H. And so going any further than this, it's difficult to have supernovae that are observed in many bands, but there's a reasonable number of supernovae that have observations in these bands. And also supernovae that have data at maximum and various other selection criteria. And then when we had this sample, Nico then went on to derive nickel 56 masses using this classic Arnett rule. Using a new formalism, a new analytic relations by Katami and Kaysen, they claim gets around some of the problems with the assumptions in the Arnett rule, and also the tail luminosity. So I said you can't use the tail luminosity, but you can still use it as a lower limit, because if you have some, you have a photometry here, you have your barometric luminosity here. You say, okay, let's assume that this can give me the nickel mass. And then whatever nickel mass you have will be a lower limit because you're not fully trapping the emission from the radioactivity. And this is important. So if you want to know absolute values, obviously this a lower limit only gives you so much information. But if you want to compare to the type 2s, then this can still be very useful. So I show these values here. So the Arnett value gives this 0.08, and then it's Katami and Kaysen 0.04. It's interesting this is lower than the tail because that doesn't really make sense. And this is, I think this is again some assumptions of the Katami and Kaysen modeling that are probably not right here. But the tail luminosity 0.05 solar masses here as a lower limit, I think is really, really robust. And so this is now a plot like I'd shown here. Sorry, the colors change here because this is Nico's plot. We didn't keep things consistent. But here I have the same type 2 samples. This again, nickel mass on the x-axis, cumulative distributions. The same type 2 sample that I took from the literature. But now this is Nico's Mesas stripped envelope sample. So a smaller sample, 35 supernovae here, but well observed, good wavelength coverage, etc. And then in the black is using the classic Arnett rule. And so we still see a really statistically significant difference here between the black and the red. And then in the blue, the Katami and Kaysen, and then the green, this tail luminosity lower limits. So these are much closer now to the type 2 supernova distribution, but there's still a statistically significant offset. Another thing to notice here is that there's no longer any of these crazy values here. So this could be for a couple of reasons. One reason, is that, okay, when you make cuts on your data sample, data quality, maybe you remove supernovae that don't have high quality data, and it was the fact that they didn't have high quality data that led through some systematic to them having these really high nickel mass estimates that seem unrealistic, at least within the paradigm of core collapse supernovae being driven by this neutrino-driven explosion model. Or the other option is, when we derive a well-sampled, well-observed sample, then we basically limit ourselves to very local events where you have a better chance of observing them better. And then in that case, rarer events and maybe these rare things that have lots of nickel are more distant because they're rarer. And therefore we just don't have them in the sample. So either one of those is possible. Also in this paper, we analyze a range of observational systematics, such as the volumetric correction, the distance, explosion, epochs, and these change things around. And at the extreme ends of changing these, you can say, well, or maybe almost it's consistent, but you're really pushing things. And I don't believe any of these things can produce the large differences we see between the type 2s and the stripped envelope supernovae. What is really seen here is now that it's very clear, at least with this sample, that's what's driving this is this bottom left here, which is the lack of low nickel 56 mass stripped envelope supernovae. So, while at higher values, then the distributions are more similar, but these lower values, you have things for type 2s that go down to very low values, 10 to the -3 solar masses. Whereas for the stripped envelope events, you have basically very little that goes down below like 0.2 solar masses here. So then the question becomes, is this true? Is this a real difference between the different supernova types? Or is this an observational bias? So is it different progenitors or explosions or an observational bias? If it's an observational bias, I mean, this is things I came back to. So why could this be different between the different supernova types? I think because for the stripped envelope supernova, the peak luminosity, so the maximum luminosity that you'll observe, so it basically determines how well you can detect these in your surveys, in magnitude limited surveys, is dominated by how much nickel the object has. Where in type 2 supernova, you have this initial phase, which is dominated by other energy inputs. And so the effect, if it exists, well, it does exist. We all know, such observational selection effects exist in astronomy, but that it exists and it preferentially affects the stripped envelope supernova population is a possibility. And I realize that I'm running out of time now, so to not take you on so long, I'll actually skip over this here, but we are actually working on this. So this is a paper in preparation by another student, Ryoma Ouchin, a student at Keiichi Maeda, where we make some simulations on this. And at least my interpretation is this, that yes, this affects things, and this could explain some difference, but I don't think it's the whole case, and it still struggles to explain the really low nickel mass objects, but I won't go into the detail of explaining this plot. So progenitor, so if this is not, in my opinion, this is not, a systematic in how we're modeling these. This is not a systematic, at least it's not dominated by systematic in observations. So therefore, this implies maybe differences in progenitors. So difference in progenitors, a difference in the pre-supernova inner core structure. So does this mean higher mass progenitors via zero each main sequence mass progenitors supernova? Possibly. And there is some evidence from explosion models that suggests more massive progenitors produce more nickel, although it's not a one-to-one correlation at all. Or in binary interaction, there's a larger degree of binary interaction in stripped envelope supernovae. And so the question then is that, but does this affect the core? Does this affect the area where this nickel is being produced? As I said, I think a few years ago, I kind of naively assumed that this was not the case. Because I assumed that when you have binary interaction, most of that interaction is dealing with the outer envelopes and the outer ejector of the star. But we'll see the next slide I have plot on this, suggesting this is possibly not the case, at least in some and maybe many progenitors. No, the other possibility is that maybe different supernovae have different explosion mechanisms. So, maybe this assumption that the majority of core collapse supernovae are being produced by the same standard neutrino-driven mechanism is not correct. Maybe in some stripped envelope supernovae that have these very high nickel masses, maybe there's a different powering source there. And so if you have a different powering source, if you have some additional energy, so you maybe have some nickel produced in the center of the explosion, but you also have some different additional energy from a magnetar or some from accretion onto a neutron star proto black hole, then maybe this boosts the luminosity, and therefore you don't have so much nickel, but then your nickel, so the nickel constraint you have is not correct, but then it's separating the triple envelope from the type 2s of having a different explosion mechanism. And this is quite likely the case for at least the stripped envelope, the 1C broad lines, and those that are related to gamma ray bursts. I think this is, it's almost accepted in the community. But for the more normal stripped envelope supernovae, at least at the moment, we don't usually discuss these as having a different explosion mechanism. Okay, last slide before I get onto my summary slide. So this was this point I was making about whether binary interaction can really affect the core structure. So there was this paper out last year of looking into this and looking how single stars compare to binary stars in binary systems in terms of how they explode as core collapse supernovae. And here they do indeed show. So if you look at the right-hand side plot here, this is distributions of nickel masses. If we just concentrate on the two blues, so the dark blue is single stars, the light blue is a certain case of binary interaction, binary mass transfer. And indeed, in the binary transfer, the amount of nickel produced is biased to slightly larger values than the single star case. So I don't think this is the end of the story here, but this possibly could explain these differences we're seeing here. But it's not clear this explains the large values again. Again, you see nothing higher than 0.2 here. And it's also not clear whether this explains this lack of really low nickel masses that we see in the type 2s. Okay, so this is my summary slide. I won't go through all these things here, but I think, my opinion is that the stripped envelope supernovae that we have observed to date eject significantly more stripped nickel 56 than the type 2 supernovae, the ones we've observed. I don't think this is completely driven by systematics, although systematics are at play here and has explained some of this difference. It maybe implies a population of low luminous stripped envelope supernovae that are being missed. And indeed, I had a discussion with one of your students, Win, this afternoon about general things, these discussions that you guys invite us to have. And he was on a paper on some peculiar, he led a paper on a peculiar calcium-rich object, supernova 2019 EHK, I think, which indeed had an extremely low nickel mass compared with other stripped envelope supernovae. I mean, that's in no means a normal stripped envelope supernova, so it's not clear how that fits into this picture, but maybe there are some strange things going on there that should be included. I think a true difference in nickel mass implies real differences in progenitor inner core structure. The question of this is, does this come from mass differences or does this come from binarity? And I still think we have these extreme values that it's hard to explain through standard core collapse supernova explosions. And then the last point I want to make here is that, I came into this through these kind of informal discussions at conferences and things like this, or looking at different papers and saying, no, there's something strange going on here that we're not really, as a community, not really discussing here. And, the analysis was really simple. This is not me being some genius in the way I've modeled supernova or anything. This is the simplest analysis you could imagine. But to me, it gives significant insight, or at least motivates more discussion in the community, and discussion that wasn't being had, and has led to a number of papers discussing this and trying to explain the difference that we see here. And I think this is important going forward, not just for work here, but this is important going forward as we move forward to having ever more data. We're going through to the era of LSST survey, which is going to have many thousands, millions more supernovae. And it will be very easy for us to, publish even large sample analyses that have, very interesting results, but in a very narrow definition that's only applicable to that specific supernova type. But I think what's important is that we don't lose the focus here of how we tie in these new results, how we tie in these single supernova studies into the global picture. And yeah, with those last words, I will finish. Thank you very much.